Good morning, everybody, and I'd like to welcome all who are here at USCAR and online to the USCAR Advanced Battery webinar. I'm Steve Zimmer, Executive Director of USCAR, and in addition to introducing the webinar, I'll be your host throughout the next hour and will moderate Q&A following the presentations. This is the first of what we hope will be a new and informative series of webinars covering various technology areas in which USCAR is involved or in possible new opportunity areas where collaboration exists or can evolve. I want to thank Stacy Boyle and Susan Barley for all the work they did to figure out how to use this technology, and I apologize in advance if we have any glitches. We hope we won't, but we may, so we'll go through that. Our presenters today are Stephen Clark. He is the Chrysler Group representative to the United States Advanced Battery Consortium, USABC, Management Committee, and he will give the first presentation, and then he will be followed by David Howell, Team Lead, Hybrid and Electric Systems Vehicle Technology Office at the U.S. Department of Energy. And then wrapping it up will be Jeff Chamberlain, Deputy Director of Development and Demonstration at the Argonne National Lab. Each presenter will give a overview of their organization's role and perspective of advanced battery research and development. And all three presentations, once they're complete, will follow with questions and answers. So with that, without further ado, our first presenter is Stephen Clark. Stephen.
Okay, good morning. Let's jump right into it. There we go. So our mission is to develop electrochemical energy storage technologies that support the commercialization of hybrid, plug-in hybrid, electric, and fuel cell vehicles. And this is done with funding through a cooperative development between the USABC and the U.S. Department of Energy. And this cooperation allows for the combined technical and financial resources of the DOE, the OEMs, our development partners, and the U.S. national labs to jointly conduct this advanced battery research and development. Some key milestones along the way with respect to the USCAR history. The USABC first got its start back in 1991 and is one of the early USCAR consortiums along the way, and that's been active through PNGV, Freedom Car, and most recently the US Drive partnership. So looking at an overview of how we're organized, the USABC has a management committee which is comprised of myself, Ted Miller from Ford, Mark Verbrugge from General Motors, and Dave Howell from the U.S. Department of Energy. And then under there we have a technical advisory committee and then the active work group members that are responsible for development and program management activities. In a parallel organization under the USCAR, we have the Electrochemical Energy Storage Tech Team, and it's the same cast of characters for the Technical Leadership Council for that group, but they're set up a little bit differently with regard to the tech team activities. Ken Snyder and Dave Howell are co-chairs for those activities, and each of the members that work in that organization are responsible for overseeing and helping out the DOE with some of their battery research efforts that are undertaken separate from the USABC organization. So how do we do this? Starting up in the top right, the funding comes from the DOE and the national labs, and we get their government perspective on what the administration's wishes are. Then our development partners, we work with battery suppliers to develop the technologies, and we get their technical expertise and real-world cost data, manufacturing capabilities, and to prove out the feasibility of these technologies. Those are tested at the national labs, and we end up with real-world data, and we're able to benchmark as to how those technologies are doing against our goals. And the automotive OEMs, we bring our technical expertise and most effectively the program management of the USABC programs. And then we're also involved in developing some of the test methods and giving the requirements a real-world perspective. So looking at some of the histories and successes from the USABC, lead acid back in 1990 was the first shot at EVs. That morphed into nickel metal hydride version of EVs by the end of that decade. And that first shot didn't quite stick commercially, but I think that genesis gave us a good effort as to what really is required to make a electrified vehicle feasible. And then lithium-ion has been our focus since early in the decade, and those batteries are now commercially available in vehicles like the Chevy Volt, Ford Focus, and some of the other vehicles that are out on the road today. And we're looking in 2015 towards advanced batteries that are lighter, cheaper, better energy density, whatnot. So let's go through a little bit of the program goals and how we do our work. So we try and define the requirements in metrics such as an example here on an HEV would be to give 300 watt-hours of usable energy with a discharge power capability of more than 25 kilowatts for 10 seconds at a cost of less than 20 kilowatts or $20 per kilowatt. And that kind of sizes up what we expect to see from developers. Another example on a PHEV would be to supply 3.4 kilowatt hours of usable energy or about 10 miles of all electric range with discharge power capability greater than 45 kilowatts at a cost of less than $500 per kilowatt hour. So you can see we're looking at power, energy, cost, and the different metrics there. So those goals are intended to represent values which would be competitive with internal combustion engine vehicles on a cost and performance basis. So our program activities are working with our cost share partners in industry, and all of our contracts have at least a 50% cost share with the developers. And those developers are working on those electrochemical energy storage systems against our goals. And then we also are working to develop the test procedures for those storage devices as to how they're tested. And those tests are undergone at the different national labs. We use the Argonne National Lab, Idaho National Lab for performance benchmarking, Sandia, most notably for their abuse testing capabilities, NREL for thermal analysis, and then we also work closely with some of the other USCAR consortium teams and ANL and NREL to come up with some of those vehicle system approaches. So looking at some of the status of where we're at today, the spider chart kind of shows where we are in a relative sense. This blue line around the circle here represents 100% of goals. And you can see in certain areas we're exceeding the goals for things like self-discharge and volume. This is for an HEV power battery. But you can see we're falling short in things like cold crank performance and cold temperature, production piece price. And so we've still got some work to do in some of these areas. Looking at the PHEV battery status, we're doing pretty well in certain areas, but we're falling short again on production price, some of the cycle life capabilities, and the system volume, which feeds back to energy density. Looking at the EV status, we've got quite an aggressive production piece price goal, so we're a little shy there. And then the rest of the power and energy is not too bad, except for when it comes to energy density. Those areas we're still working on, and the cold power is also a challenge. So looking at some of our program focus and trends, in the past we've been focused on HEV battery development, and that we think is at a point where it's commercial, and we've focused now more on higher energy EV and PHEV battery development. We were doing low-cost separator development, and then we've now morphed into improved abuse tolerance separator breakthroughs, looking at things like ceramic coatings and other things to help improve the abuse tolerance, and then improved active materials for some of the low-energy HEV energy storage systems. So we also have the USABC request for proposal information. We have under a new cooperative agreement with the Department of Energy, we're issuing RFPIs for 4 different areas of battery development for EV applications, 12-volt stop-start vehicle applications, plug-in hybrid applications, and a new category in 48-volt mild hybrid applications. So those RFPIs, I think the 48-volt one will come out in advance of the others, but all of them will be issued in the next month or so. And we're looking to get feedback from our developers on those proposals. So our technology challenges that we have for the future, calendar life is still a challenge to be able to make a battery last for the lifetime of a vehicle. Cost is probably one of our toughest goals to meet. We've got some very aggressive cost goals for our battery systems. Abuse tolerance, because the safety of the batteries is primary for their adoption within industry. And we still have challenges in low temperature power performance. So in summary, the government and industry collaboration is very effective at advancing some of these energy storage pre-competitive technologies, and the USABC has been successful in advancement of vehicle electrification. If you're interested in getting more information, there's a link to our USCAR.org website for the USABC team, and under there they have program goals, cost models, RFPIs, test procedures, and different information available. So next up, we'd like to introduce Dave Howell, our representative from the Department of Energy.
Again, I'm Dave Howell. I'm with the Vehicle Technologies Office here in the Department of Energy. I wanted to provide you an update of some of the work that we're funding at the Vehicle Technologies program. But I actually wanted to start first with an overview of all of our energy storage work that's related to electric drive vehicle batteries here at the department. As you see, it starts in the Undersecretary of Science and Energy. We have 3 program offices that fund work in this area. The Office of Science, Basic Energy Sciences. They tend to fund the fundamental research to understand and predict and control matter and energy at electronic, atomic, and molecular levels. When you think of the Office of Science work, you think of the J. Caesar Hub. The funding for the J. Caesar Hub that Jeff Chamberlain will speak on here in a few minutes comes from the Office of Science, or the Energy Frontier Research Centers. We refer to them as EFRCs, and Core Scientific Research. For the Vehicle Technologies Office, ours is an applied battery materials and cell optimization and pack optimization R&D effort to enable a large market penetration of electric drive vehicles. Our work, typically things that you hear us funding are things like USABC. Steve just discussed in detail some of the work at USABC. The BAT program, or what we call our Exploratory Materials Research Program, it's an applied battery materials R&D effort funded out of our office, where we fund universities and laboratories to develop new and improved materials. And things like KBAT, our computer-aided engineering design work for batteries, developing the virtual design tools needed in order to cut the time to design and demonstrate vehicle battery technology. The third area of funding is under the Advanced Research Projects Agency for Energy. They fund high-risk transformational research with potential for significant impact, significant commercial impact. You hear terms like ANT, which is a battery controls portfolio, or range, which are new battery concepts such as flow batteries, solid state, and multifunctional batteries. If we start looking at our battery technology research roadmap for the next 5 to 10 years, as you see here on this graph, the graphite anode with a layered type cathode or a spinel cathode or an iron phosphate cathode is what's being commercialized today. Typically see prices around $400 to $500 kilowatt hour for PHEV batteries in this area. But there's quite a few other technologies in the lithium-ion family that look very promising. One would be a lithium-ion battery with high voltage or high capacity cathodes, and that would be coupled with the graphite anode. Or secondly, a lithium-ion battery with a silicon metal alloy anode, coupled with a high capacity cathode. Both of these look to very promising for future development. Another area is in the lithium metal systems. Lithium metal anodes with or lithium coupled with sulfur cathodes, or even lithium air and non-lithium systems. The vehicle technologies programs focus most of our support on the lithium-ion technologies, the Gen 2 or the Gen 3 type technologies. We have some exploratory research effort going on in lithium metal systems, but fundamentally most of our program is focused on lithium-ion technology. If you speak about the Office of Science, their focus is actually beyond lithium-ion, lithium metal systems, lithium sulfur, or even lithium air and non-lithium, and new battery concepts. And if you paste where the ARPA-E programs fit within this roadmap, you see the ARPA-E range is developing new battery concepts. The ARPA-E BEAST program that was started was focused mostly on the lithium metal systems, and the ARPA-E AMPed program, again, looking at battery controls to actually increase the capacities that you can actually use in today's current batteries. Our goals are shown here. 2014 to 2015 range, we would like to demonstrate battery technology that could achieve $300 per kilowatt hour, and that's with meeting our battery performance targets that Steve had mentioned in the previous presentation, and in 2020 actually knocking that down to $125 per kilowatt hour. So we've made a lot of progress in the last 5 years with our USABC partners. Particularly, we've been able to reduce the cost of lithium-ion batteries by 70% on a dollars per kilowatt hour basis, and double the energy density of PEV batteries, as you see on the chart over to the right. The results were on prototype cells and demonstrated hardware that were tested against the DOE USABC performance targets, and the cost was derived from a battery cost model, the USABC battery cost model for PHEV battery packs that would be manufactured at a volume of 100,000 per year. We still have work to do on these systems, but this is very promising to us, and particularly because of this next box here. These batteries range from PHEV 40 packs, 14 kilowatt hour, to EV packs, 40 kilowatt hour. Relatively small packs on an energy basis. But more importantly, the battery development projects focused on advanced cathodes, processing improvements, cell design, and pack optimization, with standard electrolyte and graphite were used in each of these. So we see new technologies that we're developing that could actually push the performance of these systems, particularly on the energy density and specific energy range, and potentially on cost. We have done quite a bit of analysis in conjunction with the Energy Storage Hub, the JCESR Hub, to try to understand how far we can actually drive the cost down with new battery technologies. As you see here, just the first bar in the graph to the right, that's typically the graphite NMC type material. The theoretical cost would be about 200 to 10 if everything was met and if all chemistry problems were solved. And that's for a very large pack, 100 kilowatt hour pack. But you see, as you move over to the right on this chart, you see new technologies that could actually have the potential to meet our cost targets. As I said, these are the best case projections. All chemistry problems would be solved in this case. Performance is not a limiting factor. Favorable system engineering assumptions were made, and high volume manufacturing was modeled. The point here is it just gives us a lot of hope that if we're successful in our R&D approach and our R&D programs, we can move toward or possibly even achieve our cost goals. So the Vehicle Technologies Office battery R&D portfolio, just about every project could fit in one of these three categories. An advanced battery materials research project, where you're trying to improve the capacity of materials, trying to mitigate failure in the materials level, focused on advanced anode development, cathode and electrolytes, doing a lot of scientific diagnostics and material modeling to achieve our goals. Typically, these types of systems are demonstrated on very small lab scale cells, 10 to 100 milliamp hours. And it's mostly a laboratory university type effort, although we do have some industry entities like Daikin and Hydro-Quebec and 3M and Wildcat Discoveries involved as well. And you see here on the left some of the types of systems that we're focused on, the intermetallic anodes, and even developing new binders, layered oxides, high voltage spinel, next generation electrolytes, including high voltage or solid polymer, developing electrolytes for lithium metal systems, trying to find ways to develop non-flammable electrolytes. And in this portfolio, we have some of our beyond lithium-ion research on lithium metal systems, things that would inhibit dendrite growth, or to allow efficient utilization of sulfur, or bifunctional catalysts for oxygen electrodes. In the middle portion here, where we say cell design electrochemistry optimization, that's our applied battery research activity. That's actually taking advanced materials like an advanced anode and cathode, coupling those together, because these advanced materials need to work as a system, and then optimizing their electrochemistry performance. The focus here is to improve the power and capacity of the electrochemical couple, and on life improvement, particularly cycle life and calendar life. We have cell targets that we jointly developed with the auto industry and our partners here. And our typical demonstration hardware would be in a 1/2 to 1 amp hour cells. We did in 2013 award 6 new projects in this area, and as you see them here, all of these are focused on high voltage or high capacity cathode systems coupled with a high capacity anode. They're all about 2 years in duration, and just about every one of them have a very strong team associated with it, as you can see there. And moving on to the right side of this chart is our advanced battery development effort. That's where the USABC falls in for us. A lot of our testing work is focused here, and the computer-aided engineering work is focused in this area. And that's where we actually, these are the most robust cells we build and test in conjunction with the USABC. 5 to 40 amp hour cells, and sometimes even higher. We focus on pack level targets in this area, performance optimization and cost reduction. And of course, Steve gave you a very good presentation on the USABC effort. Just like to mention that we do have a new cooperative agreement with USABC. We awarded that in 2013, It's a 5-year duration effort, $25 million a year, $12.5 million cost share. And, you know, we have a very good track record of success with these types of programs. The lithium-ion battery technology that's entering the market today is muchly owes itself to some of the development work that's taken place between DOE and USABC. So, with that, we'd like to mention, some potential funding opportunities coming up in our program. Steve mentioned the USABC Cooperative Agreement funding opportunities here, the EV, PHEV, 12-volt, 48-volt RFPIs. We also have a Vehicle Technologies Office-wide funding opportunity announcement on exploratory materials research focused on beyond lithium-ion chemistries or solid electrolytes. We have a new FO funding opportunity announcement coming up on what we call the incubator program, trying to touch venture capital type companies what we call on-ramping off-roadmap technologies, funding things that we would typically not fund that would have a high payoff for our program. And of course, the Small Business Innovative Research Program we have every year. And depending on budget, we may have a funding opportunity announcement on materials processing and production improvements, specifically on Gen 2 and Gen 3 type lithium-ion materials. But most likely this is going to be put off to FY15. Our research and development is great, and particularly when it's successful, but one thing we do want to see is an industry established in the United States. Here you see we've come a long way in the last 5 years. A lot of this is due to the Recovery Act plants that were funded. But if you look at circa 2008, we had a lot of R&D facilities in the United States, very little production, some production in North Carolina on materials, lithium metal, and separator technology. We had some small specialty manufacturing groups around the country. But today you see a huge difference in the map. The red states show where large-scale manufacturing has been established. And then, of course, materials production capability in the yellow is actually, progressed quite well. And we have a lot of new startup companies in the battery space. So we're very encouraged by this. We've got a lot more work to do. But, one thing we do want to see is domestic manufacturing of batteries. Just want to leave you with a couple of slides on where you can get more information in terms of all of the projects that we fund in each of our technology areas, whether it's exploratory materials research, applied battery research, or even the USABC programs. We have an annual progress report that describes in detail some of the progress that's been made in each of those activities. We also have the Vehicle Technologies annual merit review, oral presentations, and poster sessions in mid-year to reflect upon the progress that's being made. And lastly, we did update our energy storage partnership roadmap this year with US Drive, and it describes our ongoing and planned R&D efforts for electric drive vehicle batteries. It has our performance goals and cost targets listed as well, and it's organized in 2 different areas, as I mentioned before: next generation lithium-ion materials and beyond lithium-ion. And with that, I'm going to turn it over to Jeff Chamberlain.
Okay. One quick introduction. Tony's going to get in the screen real quick. I have with me, thankfully, the head of our battery department at Argonne, Tony Burrell. Most of you know him. Again, my name is Jeff Chamberlain. I'm deputy for demonstration, development and demonstration in the Joint Center for Energy Storage Research, the battery hub that's run by Argonne. And I wanted to start by saying I have a lot of slides, more than I could actually get through reasonably, because I know they'll be published. So I'm going to skip through several of them. But I want to make sure that 3 points are made. One is that we do work, as Dave and Steve have already mentioned, in lithium-ion and beyond lithium-ion, with the intent of continuing from a research perspective to fill the innovation pipeline. So filling the innovation pipeline with advanced lithium-ion, and then looking even further in the future to fill the innovation pipeline with things beyond lithium-ion. That's point number 1. Point number 2 is that we do have collaboration across the United States in research, and that system, that research system that's a collaborative system, is becoming real. That's really point number 2 that I hope you see in the slides I'm going to show you here. And then the third point is that we do this work in service of the investor. And the investor in our case is the U.S. taxpayer. And what we mean by that is the ultimate service to that investor, the taxpayer, is to perform research that enables the supply chain that Dave just mentioned to develop product. So our aim is to do the very basic research as well as the materials discovery and design that will enable product in the supply chain to be made. That said, the Argonne program does, as I mentioned, span lithium-ion and beyond and connects programs across the United States, and specifically in lithium-ion, which is, as you know, more mature than those technologies beyond lithium-ion, materials discovery and design, pre-pilot engineering scale-up of materials, cell fabrication, including connecting to further engineering R&D at Oak Ridge, performance and life testing, which was already mentioned, connects to Idaho, as well as connecting to the abuse testing at Sandia, as well, and then finally post-test analysis. And in 3 of those 5 bullets, we do also not only experimental work, but modeling work, some of which Dave showed coming out of J. Caesar. And then finally, we also do work on and beyond lithium-ion for materials discovery and design, and that is both funded by the Office of Science as well as EERE. Why isn't this working? Okay, I really hope everyone on the phone knows what a lithium-ion battery is, but we include this in every one of our presentations. You can see the animation of ions moving back and forth from cathode to anode. And really the point here is that there are problems that we want to address from the materials perspective in the anode, the cathode, and the electrolyte. And I'll start with cathode. This is a graph that describes the electrochemistry, both the beneficial electrochemistry as well as the troublesome electrochemistry in lithium-rich NMC, which is being commercialized around the world right now. And there's a reason I use it as one example of a success of the kind of research. Our first patents were filed and publications came out in 1999, 2000 timeframe. Another step we're taking in the cathode development for lithium ion is to look at graded materials, with the idea, the essence of the idea being that you could vary the components of the materials that are overly active with the electrolyte inside of the particle, and then put the materials that are less active against the electrolyte on the outside of the particle, so you can mitigate the activity while still aiming at a higher overall energy density. And that work is funded by ERE. And again, we're publishing these slides on a website later for USCAR, so I won't go through all of the details. But we're looking at moving beyond ordinary particles into these graded materials. In the anode materials, there are a few choices to look at in lithium-ion, and again, everyone in the audience here knows these choices. Graphite and other carbon materials are used today. We want to look at moving to metals, semi-metals, and intermetallic compounds as well as metal oxides. And to give a couple of examples of what we mean by materials discovery and design, I show here a compounding of graphene, which is a certain form of carbon, with silicon. And what you see is these little balls here are silicon connected in with the conductive graphene, with the idea being that you can mitigate or engineer around the effects that we suffer when silicon expands during lithiation or contracts during delithiation. So if we can couple that with a material that's conductive as well as flexible like graphene, we may be able to get the higher energy density of silicon and prevent the failure modes caused by that lithiation-delithiation event. Similarly, we're looking at 3D architectures, building architectures that can be connected to current collectors on which we can build anode materials, whether that's metallic compounds or silicon, so that we can account for the expansion and contraction by having open interstices inside of the 3D architectures. Again, these are just examples of what we mean at Argonne by performing the material science to identify down at that molecular level what materials will work in lithium-ion batteries. And Tony may chime in on this, but there is an example we have in our existing program for lithium-ion that really, in my view, shows two things. One is the deep science that can be performed in the laboratories to answer hard questions to enable commercialization, as well as the kind of collaborations that are happening this last decade. We've moved more and more towards collaborations and coupled those with individual research. And Dave will be the first one to point out that it's no surprise that the Department of Energy is moving us this way by opening calls, and USABC is as well, by opening calls that in essence force the collaboration. The funding is in some cases counting on or requiring collaborative efforts for researchers and connecting to industry. So there are project objectives in something we call the voltage fade project. And the idea here is to improve materials level performance of the lithium and manganese rich layered transition metal oxide cathodes. And those improvements are necessary to significantly improve upon the lithium ion cathodes. So Tony here has built a team at Argonne and spanning across the country actually to look at what can we do about the voltage fade problem that we see the lithium rich NMC. And the point I want to make here is, starting with the same graphic that I showed earlier, what have we done? What do we mean by work at Argonne and across the National Lab Partner Set? For example, there was a question of, can we use coatings to mitigate the voltage fade effect in NMC? And I'm skimming over about a year's worth of research, Tony, to deliver the answer. The answer is no. And there was a wide variety of coatings technologies that were tried while we were measuring the effect of voltage fade at the cell level, at the half cell level and at the full cell level, to really do a systematic study to see whether coatings will work to mitigate the effect of the voltage fade. And the answer was no, and as a team, that enables us and the industry to move on from this question, because we really did the basic work to answer the question, do coatings help us with this problem? Similarly, we've asked ourselves the question, this was a presentation at the annual merit review in the spring, does the synthesis method matter? If we synthesize the material one way versus another, can we mitigate or solve or prevent the voltage fade problem? Now, since this presentation was given, we've discovered the answer to that is also no. That if you end up with material that is in structure X, regardless of the path we use to get to material structure X, if it indeed is structure X, we still have the voltage fade problem. And that is also an extremely important result in the field and even in the industry. I would argue there was great hope that either through coatings or through manufacturing process, we could mitigate the voltage fade problem. Moving forward, we're looking at particle level effects to determine if we go all the way down, and here you see a little graphic of a TEM picture. If we go down and study individual particles and identify how those particles are behaving at the molecular level, can we then change the structure itself as opposed to changing the manufacturing method? And one example here is using sodium ion exchange. So we start with sodium in the crystalline structure and exchange that with lithium. That leaves us with a different crystalline structure that may then mitigate this voltage fade effect. Now, we have, as I mentioned, we have materials discovery that is connected to, funded by EERE, our materials engineering research facility, where we have the ability to scale from micrograms or grams to kilograms of materials, and then connect that to a dry room cell fab facility, so we can have a kilogram of new material actually make commercial grade cells either in pouch format or cylindrical cell format, and then test them using well-known protocols that USCAR is well aware of. We also have another capability at Argonne that we call the post-test facility. I think we have a new name for that. Okay, well, maybe we do, but it's not out there to the public yet. Okay, and here we see an X-ray photoelectron spectrometer where, after testing the materials, we can understand what has happened to those materials in use in the cell. Okay, that is my quick overview of lithium-ion work at Argonne. Now I'm going to go even faster to describe what's coming next, and this is the Basic Energy Sciences, the office, BES office of DOE. funds a great effort that's led by Argonne, and this effort we call the JCESR, or the Joint Center for Energy Storage Research. You'll notice that our objectives, and again, I won't go through these in detail, but our objectives are aligned with the objectives of DOE, in that this $100, we're looking at both transportation and the grid, but for sake of today, I'm going to talk about transportation. $100 per kilowatt hour is our objective, but that is total energy. When you crunch the numbers against the numbers Dave showed, that's usable energy, it works out to $125 per kilowatt hour. One point I'd like to leave you with on JCESR is it is a team. It's led by Argonne, but it has 4 other national labs listed here, 5 universities, as well as the supply chain from industry. And what's important to note here is this is a core team, but we also have over 40 affiliates associated with the team, and the existing industrial partners do not have a priori exclusivity on any of the intellectual property that may emerge out of the Joint Center. So that we do work with them, we're going to have great innovations working with the supply chain, but we reserve the right to license others, which is another way of saying we don't want to pick the supply chain for the U.S. auto industry. We also have notable individual contributors from Harvard, MIT, Notre Dame, UTRC, and Waterloo. You'll recognize a couple of names in that, in Yetming Chang and Linda Nazer, as well as Garrett Cedar. Now quickly, I'm going to give you a snapshot. This is unpublished as to date, and we're following the juried review process to make sure that our work is sound before we disclose to the world what we've seen during this first year of startup. But we are looking at multivalent intercalation and what we call chemical transformation, which is lithium air, lithium sulfur, and the like. And just to give you a snapshot of what we mean by basic research coupled with engineering so that we can deliver knowledge of new materials and even new couples that can then be further examined by EERE-funded projects as well as industry itself in terms of commercializing. On the left-hand side here, you see that we've seen through computation screening by conduction electrons with magnesium that dramatically increases the mobility in the Chevreul phase of the cathode. Point being, we're learning some new things about how to move magnesium, a doubly charged ion, through an intercalant host that we did not know prior to the start of the hub. We couple that with, this is a precursor slide to the slide that Dave showed. If you look here at usable energy density, this is computation in a techno-economic model, and this work was done with General Motors. Against usable specific energy, you can see graphite versus NMC and how that compares to lithium metal against lithium manganese rich NMC, and how that compares to the oxygen coupled with lithium. And then finally, we already are doing some baselining prototyping of magnesium cells so that when we make new materials discovering the very basic elements of the hub, we're ready to make real prototypes for delivery to industry. I'm going to skip through some of these slides just to point out that although it's a $24 million a year project with a sum total of $120 million over 5 years, that although we're doing a lot of investigation into this fundamental material science behind the potential anode, electrolyte, and cathode materials, we do have a roadmap and milestones and management plan that is set up so that it maps out the full 5 years. And you can go through these examples later when they're on the website. They're more detailed examples of what I showed in the earlier slide, so I can get to the punchline here. One punchline, as I mentioned, collaboration really is happening not only in Tony's project in the Department on lithium-ion looking at voltage fade, but we do work in coordination with one another, and this is an example using multivalent as an example. That cathode materials discovered and synthesized at Northwestern, as well as some computation done at Berkeley, is coupled with electrolytes synthesized at Argonne and anode materials supplied by the chemical transformation thrust from P&L and Sandia to actually build what we're showing here in a schematic, a prototype device at the cell level, so we can begin testing those materials in realistic cells. And my point here is this is real. These people are all talking to each other. We talk on conference calls every other week, these sub-teams, so that the collaboration occurs and advances the science more quickly. And then finally, I point out here that one of our purposes, as I mentioned earlier, is to fill the innovation pipeline with JCESR. And we really are taking a very basic approach. I'm skimming over a lot here, but we're looking back at fundamentally the chemical reactions and the physics that occurs at the molecular level, so that when we start to think about engineering a material or engineering a cell device, we can couple that with work at ERE or work at ARPA-E or even work in the military, so that we can couple that and deliver engineered devices at early stage, mostly for the point of proving out that the materials discoveries are real. And we recognize that just means many years of research after that to turn this research into, this fundamental research into a device. And I finished just reminding you of these 3 points. We do work in lithium-ion and beyond lithium-ion at Argonne. When I say Argonne, I'm actually talking about a collaborative that exists across the country, and that, thanks to DOE and others, has in a way encouraged us to work together, and we are doing that, to the third point, in service to the U.S. taxpayer, which ultimately means in service to USCAR, US Drive, USABC, etc. That concludes my part of the presentation.
I want to thank the 3 presenters. I thought that was really outstanding. And so we don't have a lot of questions up to this point in time. I guess I'll just generate a question. I said, Jeff, you talk about this coordination. You kind of got Jay Caesar in the middle. I mean, how does USABC and David fit in that overall, coordination of all of those different entities getting together? Is Jay Caesar pulling together, or is it VTO?
That's a very good question, and Dave can chime in on the answer to this as well to make sure I get it right. But the reason Jay Caesar is centric in that graphic is because it's basic research, not because it's the center of the universe in terms of all the work going on, but that our belief is that from the basic research we need to deliver that out into the environment. So that's what that graphic really means. Now, to get to your question, there are a couple of things. One is that we have many people in the field that are inside of Jay Caesar that also work for ERE and ARPA-E with ERE and ARPA-E funding. But the connectivity, in my view, is really driven by DOE. They have something they call a tech team that is made up of Dave and Tien, Linda Horton and John Vetrano at the Office of Science, as well as Ping Du, is that his name? At ARPA-E. And Dave, I encourage you to comment on that. I mean, we're doing work outside of DOE to make sure the programs are all connected, and we even have an office inside of Jay Caesar that's specifically dedicated to ensure that communication happens. But really, it's driven out of Washington, if you want to comment on that, Dave.
Yeah, let me just briefly comment on it. We do, Jeff mentioned that we do have a DOE internal tech team. We meet about once every 6 weeks, or when necessary, if we need to meet before every 6 weeks, to discuss what our progress is in our each respective area, to discuss what our plans are coming up with program reviews, management reviews, and also funding opportunity announcements. We typically will share with each other the descriptions of our funding opportunity, drafts of our funding opportunity announcements before we even put out a notice of intent, to make sure that not only the other offices are aware of what each other's doing, but to get their input on areas that they would really like to see us focus on. So we do the same for them, both Office of Science and ARPA-E, and so far it's been pretty good coordination. Both ARPA-E and Office of Science participate in our merit review every year, either through poster sessions or oral presentations of overviews of their work. So we have an ongoing collaboration. We also invite in the stationary energy storage folks sometimes, but most of our discussion is on vehicle technology batteries or energy storage devices.
And Steve, I don't know if you can hear me. There we go. I would add to that, and Dave again can comment on this, but it goes in pretty good depth. That tech team that includes ERE and BES and ARPA-E meets with the Jay Caesar management team on the phone once a month, so that we do give some pretty good in-depth detail about our plans in Jay Caesar to make sure that it enables the ERE programs as well as out to the extension of USABC in the long run. And so even though we're an Office of Science managed hub, the tech team really is very knowledgeable of everything we're doing so that this coordination can occur.
I got one question. I found that map very interesting on the expansion of the supply chain from basic R&D to actually manufacturing, and it seems like there's a lot of progress there. But I know that the U.S. supply chain in this battery space is extremely challenged. So I mean, when you look at that map, it seems like it's good news, but I suspect there's quite a few gaps there. And is that just, how is that happening? How is that expansion occurring, and what do we need to do to further it along?
Well, that's a very good question. We've come a long way since we actually started focusing on lithium-ion technology for hybrid vehicles, starting all the way back to the late 90s. Started focusing on lithium-ion in the portfolio in the early 2000s. Had a lot of success. At that point, there was very little lithium-ion battery industry in the United States. As the electrochemistries became interesting and started performing in a way which was relevant to the electric drive vehicle industry, you saw more and more interest keep creeping up within the U.S. to be a part of that. The Recovery Act came at pretty much the opportune time for us, and that's really spurred a lot of investment. The Recovery Act dollars were actually matched 1-for-1 by industry. So the industry partners were putting up a lot of money, as well as the government, to establish this nascent industry in the United States. But it is fragile. All of these companies, all of these production plants need more business, and that really relates back to not only the electric drive vehicle industry taking off, which we've seen over the last several years, a nice increase of the market for electric drive vehicles. We need more, and when we went into this, we wanted all of these plants to be applicable to electric drive vehicle batteries, but we also gave them the opportunity to look at other markets, stationary, military, to name two. And you see some of the plants actually focused on those types of markets as well. I think of SAFT in Jacksonville. They've got military markets and industrial markets. A123 not only has electric drive vehicle markets, but they have stationary supply markets as well. So we have done some analysis on, domestic manufacturing in the United States. How do we make it happen and keep it here? And it's some detailed analysis for the Clean Energy Manufacturing Initiative that the President has announced. And hopefully in the near future we can provide a seminar on some of the results of that analysis on the vehicle battery supply chain in the United States and how can we compete.
Steve Clark, you want to comment?
Yeah, I would just say as we look at the numbers of companies that are starting up battery manufacturing in the United States, it's a mixture of companies that are centered here in the U.S. and a lot of the foreign companies, especially from Korea. They're very strong competitors in the lithium-ion industry. And we always ask the question, what does it take for you to come and manufacture these in the United States? And it really comes down to volume. So I think in the coming years, as the automakers get challenged with meeting both the carbon emissions and the fuel economy consumption challenges that are on before us out in 2017 to 2020, I think you're going to see that increase happen slowly over time. I think we kind of experimented with front-loading the system a little bit and maybe varying degrees of success there, but in general, it's really going to be driven by the volume numbers in electrification.
Thank you. I have one question. We're kind of getting near the end here, so I'm going to try to wrap it up. I really appreciate everybody's participation. And here's just a question, too, is, it relates to ARPA-E. The question was, how much flow battery work or plans in range are public? And how does that become public? Do you have any idea?
That's a very good question. Okay, we get to see, in the Department of Energy, we actually get to see some of the progress. Typically, the ARPA-E folks have, workshops where they bring all of their companies together and present some of the results. I know there's one workshop coming up on the AMPS program, January 8th, I do believe, and it's out on the West Coast. There's also a range workshop in late January. I think that's down in maybe in Orlando or Fort Lauderdale, something like that. So I would look on their website and ask when the next project reviews are happening, and see if there's an opportunity for participation in that project review. There's also the annual ARPA-E event in Washington, D.C. in late February, early March, regarding some of the work that's being conducted in ARPA-E, which includes the electric drive vehicle battery work. That's at the National Harbor in Washington, D.C.
Okay, I think we've kind of wrapped it up. I want to again thank all the presenters. I want to thank the participants. I hope this was beneficial. We're working on this technology. And I also encourage any of the people on the call and other people within USCAR and within our tech teams in that, if this type of communication is useful, we would be more than happy to sponsor more events such as this and record them and help share knowledge. So with that, I thank Steve and Dave and Jeff and everybody for participating, and have a great holiday season, and come back and solve all these target-rich problem areas. Thank you very much.
Thank you.
Okay, thank you.